think of PyData Milan as a jump spring to get to anywhere of the network's event. They're really a wonderful and great part of the Barrio. Okay. So you know. Okay, those who know. We, as PyData, we strive to hold the meetup on the third Wednesday of the month. We are actually doing it this time. Congratulations. The Python Milan meetup is on the first Wednesday of the month. In case anyone wants to submit a proposal, you can do that on the link below. We couldn't stick many more QR codes there, so you have to remember this one. To be fair, if you go on our meetup page, you will find the link to the Sessionize page. That is more a bit of a formality. You can submit one and I think re-edit that afterwards. So it's just a useful place for us to collect all the application that we receive. We would be glad to support you writing a proposal or edit it, of course, afterwards. So just for us to keep track of that. Can I move on? Did anybody scan? I take it as a yes. Okay. So, next event. Next week we'll be in Prima di insurance company, yes, which is in Loreto, wonderful place, amazing Chinese restaurants in the nearby, so do not hesitate. We are going to have the event really soon, but it's going to be a blast. We're still going to have like this mixture of languages and people talking about programming languages as we usually do, at least since 2025. Our next PyData Milan chapter meetup will be in AWS on the same day as today, so Wednesday the 19th of March. We will have two wonderful speakers, including scikit-learn's maintainers that will come specifically for us to talk. So please do not hesitate to reserve your spot. The event will be up soon, so keep your focus on the channels. Some duly noted thank yous that I need to give to our wonderful hosts. We've found an incredible community of companies that are eager to support us. And if you want to join, if you want to be any one of the other companies willing to support and host your events, we would love to have you there. If you want to support us in any other way outside of giving us a venue so that we can invite a new speaker from abroad, please stay in touch. We would love to just bring speakers from abroad as we've been doing for, I think, like the beginning of the season mostly. We always try to have someone coming from abroad. This time it's Alexander. We'll tell you a bit more about him really soon, but it's really great to have this broad panel and bringing people from the community and from outside of Italy so that they can come and enjoy their time in Milano. Last but not least, we would like to thank you Python Italia, who supports the Python Milan chapter and PyData Milano chapter indirectly. They do organize the PyCon, the conference in Italy. This time will take place in Bologna from May 28th to May 31st. So do not hesitate, the tickets are up online, I think, for grabs. The lineup is amazing, and I'm not telling that because I'm speaking there. We also would love to support and thank Division Lab, who supports us with the recording equipment. Julia behind the camera is our video man tonight, but usually that seat is taken by Alessandro, who sponsored and gave us the recording material, as well as Python Italia, who gave us the material to record the podcast, because we also have one of those. Cesare is the host of Intervista Pythonista, only in Italian, but many of you should know it already. That being said, enough of my bantering. I would like to welcome on stage our first speaker. Alexander is going to talk about speeding up linear regression with smart algorithms. After he's done, we will take a short break just to swap the live, and we will have Fabio Lipreri, a colleague of mine, AI engineer in Extreme, we're talking about how to build an LLM as a judge that allows you to evaluate your RAG in a robust manner. Enough of that, let's welcome our speakers.
Sono un po' confuso questa roba. Sento un po' tipo John Travolta.
Presentation mode, where is it?
Se si è allontanato il cameraman dalla... Ciao, come va di corsa? Sembra giugno.
It should be.
Yes.
Cos'è successo?
Sì.
I should be sharing, right?
Ah, il video ninja. Il video ninja. Certo, devo farlo anche fare a Fabio, se no sono craxi acidi.
currently not seeing it.
Mm-hmm.
Don't know if
Okay.
it's a matter of...
And maybe just go out and in again.
Okay. Oh, I will let you know.
Okay.
No. Avrà spento il computer. È attaccato il link?
Riscerato da capo adesso.
Ci sta, sì. Il link è lo stesso. Che si mette un microfono.
Poi data.
Okay. Hi.
Hold on. No, è l'altro, mi sa.
Questo io lo sento lui che parla. Questo poi è spento adesso.
Però sta prendendo.
Ah no.
Okay, aspetta, hold on a second.
Che cazzo. Sì, quello proprio.
Ha fatto push o pull?
Push, vai a controllare.
No, ma mi fido di te, lo sai meglio tu di me.
Sì, è push.
Mettiti full screen. Luca.
You're engineers, but not that kind of engineer.
È sul Firefox. L'altro browser.
these things. I am an economist by background. I studied that. Struggling with big data sets. I will show you why slightly later. I tried Spark. It took a long time to get Spark. So I learned a lot of it. You can think about it here. Very simple regression models, like really the simplest models that you can imagine. Okay, so okay. Sorry about that. And so, okay, like this. Ah, shit, I pressed on it again. Yes. No, but... Okay. Yes? Oh, amazing. All right. So basically you can picture myself sitting in front of my laptop trying to do things after I got like very big data set out of the database. I was trying to do stuff and it wouldn't work because data sets were too big. I would get out of memory errors all the time. I couldn't fit my regression models, but I really wanted to. So then I tried to figure out a little bit, okay, what can actually be done to fit regression models on extremely big data sets and also in a somewhat performing way. And basically I'll present to you some of the ways that's possible. To just get a kind of feeling of the room, who in here has a background in statistics, social sciences, who's more on the ML engineering side? Okay, so okay, then some things should be familiar. All right, so and basically we start at the very beginning, right? So like we go from this guy Gauss, who more or less invented the least squares estimation back in I think the 18th century, might be early 19th, to AI models and how to deploy them. So I think this is a nice parenthesis overall. Okay, but so why linear regression? Why I'm so fond of it? And so I really like. Oh, actually no, I already like this, right? It's all you need to make it work in data science, at least most of the times. And so you know this meme here maybe of this general. I hope he's a good guy. I actually didn't do the research, but basically he's pitching linear regression, right? And on my screen it's already running, and we're a little bit async. So basically saying whatever your modeling problem is, there's a go-through method. Everything is approximately linear, so just fit a linear model. It's easy, scalable, flexible, interpretable, truly outstanding. You don't need all these fancy things for most things. And so this is why I'm so fond of linear regressions. I was saying my background is in economics. 90% of economics papers will use at least one linear regression. Usually it's like 300 of them. So nothing works in that research literature without them. In industry, obviously, these methods are used for analyzing A/B tests. If you want to do covariate adjustments, also you can run simple tests through regressions of treatment effects. For quasi and experimental work, it's really important. There's this entire literature on difference in difference methods, geolift experiments that are more or less powered by regression methods. So let's do some 101 on regression, mostly a refresher for most in the room. So we have this model. It's purely linear model, and we define a couple of parameters. We have this dependent variable. We have a matrix of covariates, and then because there will be a special twist to a lot of the fitting methods that we'll look at, we have this matrix D, which you can think of as a matrix of one hot encoded features. These are basically called fixed effects in the econometrics literature. In statistics, I think they would call them random effects, which is something different in econometrics, just as a side point. So these are basically big dummy variables of ones and zeros with categorical features. And then U is just the error term. And so then the basically ordinary least squares estimator that Gauss basically came up with back in 1800 something looks like this. So we've redefined the design matrix to X tilde by just concatenating the two covariate objects that we have, and then we just have a matrix multiplication. It's x prime x. We invert this, and then we matrix multiply it with x prime y. So this is super simple. You can do this in memory most of the times. It's very nice, quite convenient to do. And so more or less, this is what in R, LM would implement, or stats models OLS module would be implementing to fit a regression model. Not 100% true, but I'll talk about that later. And the main challenge with fitting this model is that basically this shouldn't be anything new to you, is the bigger this design matrix get. So the more observations you have, the higher your n is, the wider it gets, the more covariates you have, the harder it gets to do this matrix multiplication, and the harder it will be to invert this matrix multiplication, because it will be k by k. If you have 1000 features in your design matrix, you have to invert a matrix that's 1000 times 1000. Usually your computer will not like that. My computer surely will crash with out of memory error if I try. And so that's the main challenge, and that happened to me a lot in the past. Okay, and so now I'll just add basically an industry size that we're going to use throughout this presentation, and it's basically this NYC taxi dataset that you can download from, yeah, I think there's a dedicated web page for it and a lot of Parquet file for multiple years, month by month, and then you can download all of them. And we query it with duckdb, have a couple of variables, tip amount, it's like what people tip, what people pay, how many passengers you have, and I restrict the data sets to 20 million observations. Some of the methods I will show you I could run on a larger data set, but others will just fail. So this kind of industry size, but could of course be bigger. I just have 16 gigabytes on my laptop. Yeah. Okay, so but we query this, load it with duckdb and into memory, and then we have this NYC dataset. Okay, and we can fit a sample model, and this is just for purpose of exposition. This is not something that we're really interested in, not a sensible model to measure anything, but we just ask, okay, what's the relationship between tip amount and the number of passengers that we have? And for that, we define a couple of regression formulas. Basically, we regress these two features, passenger count and trip amount, on tip amount, and then we have these fixed effects that we want hot encode through the formulaic package. If you know PAT-C, there's the C operator that will basically one hot encode categorical features for you if you apply it. Formulaic is doing the same thing, and then we're just combining these two into formulas, and then basically this is the regression model that we're interested in. So what's the effect of passenger counts on tip amount controlling for a bunch of things? Okay, and we process this with formulaic, get a pretty big design matrix, could be much bigger. So now we have 20 million type 37 covariates in the model. 37 isn't really that big, but if I make it bigger, my laptop will die. So I didn't try much harder. Or this is basically, I'll show you a lot of methods later, individual methods, individual fits of an OLS regression will make my laptop die. So this is basically what I could accommodate with all the different variants of fitting an OLS model. Okay, so that's big enough. Textbook OLS fitting, this is how it looks, right? I showed you the formula. We have the design matrix X. We transpose it, and then we have XTX by matrix multiplication. We have XTY, and then we can just invert XTX and multiply it with XTY. So this is basically how you would implement this if you read a textbook and basically do this for the very first time. And then we just return this vector of confusion. It would be beta hat. And we run this just for one time. All the benchmarks I'll run for one time. I thought of doing it for more, but you'll see later that wouldn't have been very nice. And so basically this takes approximately 5 seconds. And so this is still okay. 5 seconds, we can wait 5 seconds. I fitted the same model instead of 20 million observations on 40 million. And then basically the runtime goes up to 40, 50, 60 seconds because my laptop really starts to struggle. So 5 seconds, that's a little bit annoying. And as I said before, the bigger this design matrix gets, the more likely we are to run into memory errors. And so the question is, can we make this run faster by potentially using alternative algorithms to fit these OLS models? And can we potentially make it more memory friendly? If you imagine we scale basically this data set up a lot. Instead of 20 million observations, we have 200 million observations or even 1 billion observations, right? So what is it that we can do in this case? And so yeah, we'll take a look at a couple of options for that. Before I go into this, just want to show you, if you're familiar with the basic packages for scientific computing, they usually offer different ways to do a least squares fit, or basically solve a linear equation. In NumPy, for example, you have this function here, linear least squares, which basically solves this normal equation. It solves a linear system of equations and then gives you a coefficient, and basically this is like solving an OLS problem. And so this, for example, what scikit-learn implements in its linear regressor class. And so this is basically then another way to solve this normal equation here with a QR decomposition, which is nice because you don't have to invert that matrix, so it can be overall more stable. And so here we do timings again, just of this alternative methods through this spiced function that NumPy provides us with. And here the timings. Oof. Okay, this is what you get by calling scikit-learn basically. Scikit-learn calls that function after some pre-processing, and so you wait 50 seconds. Okay, having said that, it's not always the case that this function is much slower than this one. It depends a little bit on the cases that you try out. Generally, this option here is numerically more stable. That's why all the scientific packages implemented. So it's basically safer to go with this option than to what I've implemented here. But it takes much longer in this one example that I've picked. Okay, quick question: do the coefficients match? And I'll show you a lot of coefficients of different variables, and they match exactly. So it's basically exactly the same thing that we've implemented. That's good, right? Okay, we're happy, or at least I am when I see this, because it also means that tests pass. Okay, now what are the strategies to scale up or speed up linear regression to make it fit into memory that I'll show you? One is batch regression. So you can more or less create subgroups of your data set and fit your OLS models on your data sets, and then at the end bring it all together and you get your full estimate. This would be what systems like Spark in the linear regression class implement. It's kind of nice because you can, in principle, parallelize that if you want to. We can make use of the structure of the data. Most importantly, of the fact that we have these fixed in this example that I work with. So there's a lot of zeros in the design matrix. So maybe we should try out sparse solvers for which optimized algorithms exist. We can apply a theorem that I think has been discovered by economists for the first time in the 1910s and then rediscovered by a couple of people. It's called the Frisch-Waugh-Lovell theorem. And based on that theorem, basically the entire literature in applied econometrics is built. And then we can use basically a strategy to compress our data, basically through regression compression and then potentially through sufficient statistics. And there's a couple of nice things about this to really scale up a regression. Last thing, this is about speed. We can put everything on the GPU and see if we get any speed gains. So this is basically the roadmap. I think I've talked for 10 minutes and have 20 more, so I'll be very quick. And I get a sign, please, if I have to speed up. Okay. All right. Okay. So, all right. Thanks to first strategy, we can make use of the fact that our design matrix is super sparse. So in this NYC taxi dataset that I've shown you, basically 84% of the design matrix, so it's called X tilde here, consists of zeros. So we have zeros everywhere, and that cries for using sparse matrices to do all of it. And so we have 80% here. Yeah, that depends sometimes on the size of the dataset. And so just to illustrate this again, what is a sparse matrix? Basically we have rows, we have columns, and we have a lot of zeros. Basically most of the entries are zeros, and for that optimized algorithms exist. They are more memory efficient. The key idea there is that basically you don't have to really store the value of 0 for all entries. You just have to basically store the key, and then you know, okay, of a given key everything is 0, so that helps a little bit. Okay, and so these sparse solvers, they exist in SciPy sparse. In the linear algebra module, and basically what we do now, we just rewrite the initial OLS function that we had implemented in NumPy and pull it to SciPy. And so basically the only difference here is that we have to make this X tilde a sparse matrix. Here we use a CSC matrix, Actually didn't think about this when I wrote this. This is the most efficient format for that matrix. So there's also some nuances there. But then basically we just do a matrix multiplication, x prime x again, x prime y. And basically here is where basically the sparsity, using the sparsity pays off. And yeah, here we go. So basically we just do this multiplication on sparse matrices and see if this helps. And yes, it does help. We're almost as good as the textbook model, but not really much better. Okay, so that might be a little bit surprising, but that's how it is. And do coefficients match? And yes, we get exactly the same thing. Shouldn't be too surprising here. Okay, then in SciPy you have the same to the least squares function I showed you from NumPy. You have it for sparse matrices, and it's called LSQR, that more or less implements an optimized approximate solver for sparse regression problem or sparse linear equation system. And next step, we just try that. The function is called LSQR. In my experience, it's always very fast. Now in this benchmark, it isn't at all. It's very slow. So quite surprisingly, so again, we're jumping around and we see one commonality that apparently these two functions don't help with performance much. All right. Cool. So the optimized functions, even though they are numerically safer and recommended to use, don't really give us any performance boosts here. And again, we have matching coefficients. All right. The all S fit in chunks and then bring it all together. The all S fit in chunks and then bring it all together in the end. So basically this is the split, apply, combine idea that you might know from distributed computing. I'm not sure if it's distributed computing, parallel computing. Anyways, like you split your data set, you apply a function, you bring together the results. So this is what we're going to do. And basically what we have, n observations, we just split it in G groups. So we might have 20 million observations, and we will split it into 100 groups, and we just do so randomly. So we have 100 subgroups in our regression model. And then you can just write it like this, right? So you have one subgroup that is n over 100 observations, that would be y1, y2 would have the same size, and so on, until we get to yg. You can basically write this in the exact same way. Now then it turns out that you can rewrite this equation, which is the direct OLS solution, as more or less the sum of the matrix product of x for subgroup 1 times subgroup 1 over all the subgroups, and the same thing for x prime g yg. So this looks a little abstract. I can show you how this works in code. So basically we have now this OLS batch regression, and we'll use 100 splits for it, and x and y are the initial data sets that we put in. And then we have basically a size of an individual batch that we compute. And then we just have a for loop in which over each split for 100 splits, we create basically xg and yg, which is basically the individual design matrix of a batch. And then we can compute x prime x for each batch and x prime y for each batch as well. And then at the end of the day, what we have to do is for each batch, we just add xtx g basically. So this thing we added to this result, and then we can basically use a linear solver for it. Okay, so basically what we do is we compute this here for each batch and this here for each batch, and then we sum it up in the for loop, and at the very end we invert this thing times and multiply it with this thing. We will use this NumPy function. Okay, so this is cool because if you have managed to load a very big data set into your memory, you can actually fit it. So by just chunking it into different pieces, so your regression model will not die because the individual design matrix is far too big. You can just reduce it. So requirement is you can load everything into memory once, you chunk it, and you can fit it in memory. And then if you have multiple threads, obviously you can do this operation here also in parallel. Then it would be true split, apply, combine the way I've written it here. Obviously you cannot parallelize it, but it's very easy to do. Okay, and so what's the timing? Okay, very cool. So we do much better than the OLS textbook. And so why is that? Because basically we have reduced our problem to many much smaller problems. And obviously the function I've shown you is not hyper optimized. I didn't parallelize it at all, right? It's written in pure Python. I use a big Python for loop. Maybe we should rewrite this to Numba or some other framework, and then we could potentially do much better for a bunch of problems. So this batch regression, and again, we get kind of the same. We get the same coefficients. It's just a sparse solver here. It's a numerical approximation. It's slightly off. But the batch regression gives us exactly the same results as our initial textbook analysis. Okay. You can use similar logic for streaming data. So based on an online service and you get data coming in through a stream and you want to update your coefficients in a specific way, there are formulas to update your regression models through very similar logic. And so, yeah, but I will not go into this. You can make this sparse, obviously, right? We've seen this worked quite well. What happens if we make this thing here sparse? And then we use a non-sparse solver, because basically if we multiply to sparse matrices, at the end of the day, this here will not be sparse anymore. So there's no advantage of using a sparse solver. And slightly better, right? This is one run. So not clear if this is really preferable. Okay, so where would this be implemented in the Python ecosystem? I think this is implemented, or an idea of this, in a Spark's regression module. So if you run a regression through PySpark, it's like Spark's supposed to be, I don't know anything about this, like a distributed system, right? You can fit very big models because it will run them in multiple systems. So this is all I know. Someone help me out. But so basically what it does, it should chunk the data and then fit individual components of these data. Batch regression, now the Frisch-Waugh-Lovell theorem. I will not explain it because I realize at some point I don't have that much time looking through my slides. But again, it's about making use of the structure of the data that you have. Recall that our model of interest looked like this, and we had this big design matrix with so-called fixed effects. There's a lot of problems in applied research where you actually do not care about estimating these fixed effects. And then is there an interesting or smart data transformation that allows you to consistently estimate this thing here, beta hat, without actually estimating these alphas? And so this is what the Frisch-Waugh-Lovell method allows you to do fundamentally. And so when might we not care about these fixed effects? For example, in a lot of genetic research, people are doing twin studies, and then in the regression models they would put in twin fixed effects. And usually they have another target or causal relationship that they're interested in. They're not really interested in, well, what is the fixed effect value for an individual twin pair, but in another relation, but they want to control for shared genetic material. And so they say, okay, this observation is twin with another observation, and then we would have something like a twin fixed effect. But we're not really interested in estimating it. Okay, and so without really going into much details how this works, I'll just show you how you will apply it in a few lines of Python code. And one thing that you can do is from this PyFixest package, there's a demeaning function, you can import it. And you have here in this OLS function, you have a design matrix, you have a matrix of a dependent variable, and you have a matrix of fixed effects. And now here the twist is that this matrix of fixed effects is basically the fixed effects in tabular format. So they're not yet one hot encoded. This is just the variables that you have. So we had 4 variables in our regression. So this is an n times 4 variable. And so this is nice because in your regression problem, you don't have to one hot encode before fitting, which is something that can take a lot of time depending on, well, how high dimensional your fixed effects is, like how many unique values you actually have. Not sure if you experienced this, but if you have a lot of this and put it in scikit-learn, whatever it encoded, it will take a lot of time to properly one-hot encode. And so then basically how this works is there's a specific API defined for this demeaning function. One is that you just input one NumPy array that is a concatenation of dependent variable and x. So we concatenate these two, then we put in the list of fixed effects, and then we also have to put weights there. Which is something I could clean up actually. So yeah, but we have to put weights. They do nothing. They're just weights of 1 basically. And then we demean this data. It's called basically demean by the fixed effects. And then we have demeaned y variable and demeaned x. So we call this yd and xd. And we can just put this into this NumPy least squares function. And now we've demeaned the data. and we can just do everything as before. And you see basically no fixed effects are left in here. So this is a n times 3 matrix. We have 2 covariates that survive and not even an intercept. So n times 2 is what we get. So here, this is how this fixed effect value f looks like. So we just take these for values, and because that's the API of the mean function, we have to move this into integers. This is what we do here. And then we have f. We can put this in there. And what's the timing? Okay, so slightly worse than the textbook all sfix fit, but much better than the direct least square solution. And why is it much better? Because we have a much smaller design matrix to invert. Basically, we just have 2 continuous features left after projecting out. It's also sometimes called all these fixed effects. So this is Frisch-Waugh-Lovell, and the coefficients that we have here, again, it's exactly the same as before. So that's very good. Okay, where's this implemented in Python? There's a package called linear models. It has an absorbing least squares class. If you like a NumPy API, that's basically close to scikit-learn. This is something I would recommend to you. And then there's a PyFixest package that I work on in my free time, which has a more R-like formula interface. So you put in the formula, these here would be the fixed effects, and then you can basically fit the model by one function call. So that's like a functional API, you put in a data frame. And then basically what you get out is an estimate, and unfortunately the format didn't work out. I wanted to show you that there's actually only 2 regression coefficients that pop out of the tidy method. Unfortunately, you only see 1, but there would be another one. But all the fixed effects, we don't measure them. Like we're oblivious to them. We just want to control for them, and that's it, basically. Okay, last topic. What is the time? 10. Okay, compression and sufficient statistics. So now, again, we will make use of the structure of the data that we have. And so the question is each column in our data actually a unique row, or do we have duplicates in our data? If we have duplicated rows in our data, maybe we don't have to feed all of them in our regression model, but we can basically fit them with weighted least squares, where we give higher importance to basically combinations of the dependent variable and the covariate that we observe multiple times. So this is a cool strategy in principle, because if we have a lot of duplicates in our data, we can compress a lot. Our data set shrinks massively, and that helps with basically everything in the fitting process, right? Because the design matrix is just much smaller. And so after the compression, we can then fit with weighted least squares. Okay, and so there's a saying that we sometimes use, like if you have a very big regression, at the end of the day, it can be a small regression with some weights. Okay, and so how does it look like? So here again, we have this NYC data set, and we define a variable list, which are all the variables that we have in our model. We just put this into pandas, do a group by, and count how often do we see unique, it's usually called strata, unique combinations of rows. It's like how often do we observe duplicates of a specific variant of a row, and then we sort this in ascending order. And then the way this looks like, for example, we have tip amount, we have the outcome 0, we have 1 passenger, we have day of week 2, and so on and so on and so on. And we observe this around 2,000 times. So 2,057 times we observe exactly the same column. So we don't have to feed this all in our model. We can just compress the data and then fit weighted least squares. So that's basically the idea. How big is the resulting data set? Now I have to do some. So this is like 3 million observations is the compressed data, and we started with 20 billion. So this is great, right? So let's try to do a weighted least squares fit. Just very quickly, refresher on weighted least squares. It looks exactly as ordinary least squares, just that you have this weight diagonal matrix in here and in here. And what you do usually at the end of the day, you multiply the design matrix X with the square root of the weights vector and Y as well. So I'll show you how this looks like in 3 lines of Python. So this is a weighted least squares estimator in 3 lines of Python. Okay, here's another stylized example from this paper by Wong et al., which is the reference I would recommend if this is interesting to you. Basically, we have observations m and y, that's the outcome variable, a1 and a1, basically, and then here in this table we see, okay, a1 we observe it twice, but the observation a2 combination, we only observe it once. So n is basically a count, and m and y are the features in our model, and more or less this is the group by I showed you earlier. And so what we can then do is basically do a group by here, create a count variable, use that count as weights in a weighted least square fit, and see where we land. And so this is basically what you get here. So implemented in pandas, there's some overhead through this function. Then we do a group by over the aggregation variables, which include the dependent variable and all the covariates in this use case. So we just do very simple compression. We just count, okay, how often do we have the same strata? This is what happens here. Create y, create x, and then fit with weighted least squares, basically. And here's a little bit of overhead that we need to do. What about the timing? Oops, okay, that looks very bad. Maybe it's pandas. We'll see later. Okay. But the coefficients, they match exactly the coefficients that we had before. And so this is useful if your dataset lives in a database, like data warehouse, you want to load it in memory, but you cannot load 20 million observations. Maybe you can load 4 million observations. So here, this weighted least squares and compression strategy would help you. Okay, when does compression work? Basically when the variables are non-continuous, right? So when you have continuous variables, the probability that you have duplicate rows is very, very tiny, right? If they are allowed to be different on the 10th digit or something like that. So that's bad. So in general, the lower the cardinality of your variables, the better it is, right? So if you know all your variables have only two different cardinality of 2, you can compress the data set a lot. But the problem that I have in my own work, usually we analyze A/B test, we have a discrete treatment, D, we have control variables, but the outcome variable is continuous and you cannot compress the outcome variable. And then the strategy is basically useless, right? So you cannot really do much. But are there strategies to make it work? Yes, actually there's a strategy. You can compress even more. And the strategy is called a sufficient statistics strategy. So again, you start out with these strata A1 and A1, A2, and instead of computing the count, you here compute the sum of y in a given strata and the sum of squares. And so this is called sufficient statistics. Just to give you an idea, if you, for example, analyze A/B tests in SQL, and you compute a difference of means estimator, you would always also compute the sum of your target KPI by the treatment and control group and the sum of squares of your treatment and control group. Basically what we have here is a generalization of that strategy to regression models where you're allowed to have more than the treatment assignment dummy feature, but you can have other covariates. And how does it look in code? Basically, it's the same strategy. Oh, I have it here. Okay, you cannot see that much. But basically, now we aggregate only by the covariates. We compute the sum of the variable by the strata, which are basically the unique combinations within the covariates. And we also compute the frequency. If you wanted to have standard errors, you would also add the sum of squares here. And then you can losslessly compute standard errors as well. But I'm not doing that. And then basically we run a weighted least squares regressions on the average of the dependent variable in each stratum, and we weight by the count of the unique strata combinations. Okay, that might have happened a little fast. I'm sorry about that. We can do some timings, and it's slightly better than before. And why is it slightly better than before? Because we could now compress the quite continuous dependent variable to some degree as well. So our data set that we fit on is slightly smaller again. And do we get the same results? Basically, yes, we do. So this is cool. Okay, now this was in pandas. You might say, but in polars this might be much faster. Yeah. Okay, so I implemented in polars as well. So yeah, this is okay for Luca to some degree. So yeah, we do better. We are faster, but not crazy much faster, right? Than before, and still quite a bit worse than these other strategies. But again, this is really a strategy meant to, okay, if your data set is really big and you happen to have a very small set of categorical features, then you can get a lot of performance gain with this and fit models that you basically couldn't have fit in memory before. And it does even get better than what I have described to you before. Obviously, what you can do is just do everything in a SQL language, right? You can do everything, all the aggregation steps out of memory, and then it might be very fast. It's great for basically your laptop's memory because it can happen out of memory or in the cloud environment that you're using, and then you just take out the compressed data set that you're interested in, and then you fit weighted least squares on the regress data set. And so this is implemented in a Python package called duckreg. It's powered by a duckdb library. And just to show you an example, I created a duckdb database based on the input data set that we had. Here, I have to rename the variables because duckdb doesn't allow for dots in the naming. I got a quirky error there before. So we create this database, and then we can fit the regression model as before, again, just with renamed variables to accommodate duckdb through this duck regression class, where we just define the formula again. Right now we don't compute any inference, it's pure model fitting by calling the fit function. And again, we do slightly better than before, so we slash off 5 seconds from the Polars implementation. And again, with this method, the lower the cardinality of your features, the fewer individual strata you have, the more efficient the solution will be for you. Okay. Where's this implemented in Python? Where else? We have this in the PyFixest package as well. There it doesn't happen through duckdb. In memory it happens through Polars. Funny story, I have 30 seconds for that. At some point, so I'm developing PyFixest, we switched over to the narwhals library to allow users to basically give us any type of data frame that they wanted. And at the same time, I was developing this compression feature for this compression models. And at some point, I started running my unit tests and didn't realize, as like my unit tests were taking forever all of a sudden. Like I waited and waited and waited and waited and waited. And what happened at the end of the day is that the kind of Polars implementation I had in the backend, which was now accommodating narwhals, was data frame agnostic. And I fed in a pandas data frame. All of a sudden, this was running pandas instead of Polars. Unit test ran for 10, 15 minutes instead of 1. Yeah, so there's some power in using Polars also for this, is my experience. Okay, so be careful here. Okay, so duckreg, this is basically all of the timings for this one special case that we looked at. The best performing methods is either the batch regression or the sparse regression here. Textbook is also doing quite well, not the most numerically stable, and at some point with 40 million observations, basically this also going up in runtime. So now you might ask me, why should we not always use sparse solvers to fit our regression models? Well, if you're only interested in prediction, because you're an ML person, then that's probably what you should do, unless the compression method really accommodates your problem. But if you're interested in standard errors, which is usually the case in statistics, then the sparse method all of a sudden loses some of its power. And why is that? So in econometrics, people are quite fond of heteroscedasticity robust standard errors. And you can formulate them as so-called sandwich estimators, where you have this component, bread on bread, and that's encapsulating the meat of the matrix. That's why it's called a sandwich standard error. And this meat here for the HC robust standard errors is basically the dot product of the scores, it's called, of a regression model, and that's x prime times the error term. Now, this x prime thing here, x is sparse because we have a sparse matrix, but x prime error term isn't sparse anymore. And so all of a sudden, solving like this matrix multiplication becomes very, very, very cumbersome to do because you no longer make use of the sparsity when fitting this model. And so basically here's an example with some runtime. So this takes 10 seconds to just solve this scores times scores, and a couple of other things regression. And so at the end of the day, in applied econometrics packages, usually people go with the Frisch-Waugh-Lovell solution because their computing standard errors is much faster, because basically you do not compute the full variance covariance matrix for all of your fixed effects, which is what we're doing here, but only a subset for target parameters that are continuous that we're actually interested in. Okay, so Frisch-Waugh-Lovell has some advantage there. Okay, so just to show you again, where's this implemented in the Python ecosystem, normal equations, stats models, PyFixest, scikit-learn. Usually these models have a predict model, predict methods, variance covariance matrix. You don't get this in scikit-learn, and also not with the sparse solvers, and everything works with GLMs as well. Batch regression also works with GLMs with some small adjustments. Online learning as well. Frisch-Waugh, no, this I'm actually not sure. Okay, so I take that back. Frisch-Waugh-Lovell as well. So this goes beyond OLS. Also for logistic regression, you could use similar strategies. And so this applies as well for the regression compression strategy. So you could also use that to fit the logistic regression and reduce your problem quite a lot. Okay, I didn't talk about GPUs at all. The main reason is I don't have a GPU on my laptop that I bought 7 years ago or something like that. But we're currently incorporating this in one of the packages that I showed you, PyFixest, where we're basically porting the demeaning algorithm of the Frisch-Waugh-Lovell theorem to the GPU, and basically it looks quite promising. We're using JAX, and we can, for big problems, slash off half of the runtime. And so I think if we also fit the model through JAX, then we can do even better. Okay, some advertisement at the end. So I'm involved in 2 of the projects that you've seen here, PyFixest and duckreg. So if you want to contribute, please talk to me. We have this PyEconometrics organization, and yeah, always looking for people who are excited about linear regression. Thank you, and yeah, here's some GitHub links if you want to check out. Yeah. Thank you.
Question?
We have time for one question.
Yes.
One question. So about the compression, it was basically like a run length compression which was lossless, right?
Yes, exactly. So both of these algorithms are lossless. You get exactly the same regression coefficient as on the full data set, and also exactly the same standard errors. So that's the idea behind using these sufficient statistics in the second approach. Basically, they're sufficient to characterize first 2 moments of your distribution, the basically mean and standard errors. Yeah, they're lossless.
Okay, thank you.
Yeah.
Okay. Question?
Maybe just a minor. That scikit-learn has a partial fit method that it looks like the batch regression
Okay.
implementation.
Yeah. Okay, that makes sense. I was surprised. I searched for batch regression yesterday, and I didn't find it. And yeah, it makes sense to have it.
Second thing, though, we saw that like the textbook implementation is technically faster, sometimes faster. Okay.
Yes.
How do we do when we are actually having to? Oh, sorry. Let's take a step back. I don't know. Many people were in metrics here, but that formula holds. Well, like the least square estimator is that one and works when we do have like a certain set of assumptions being verified, right? Like
yes.
the Gauss marker.
So you don't need those actually to get what in the econometrics textbook that would be called the best linear approximation to potentially non-linear fit, but that would be the best linear one. You don't need the Gauss Markov assumptions for that. These tell you something about the efficiency of your estimator, and basically, yeah.
Okay. Very last thing, maybe I don't know. Do all of these, even the like scikit-learn thing, do the matrix inversion? Don't they actually rather use like an optimizer to solve that?
So I am fairly certain that scikit-learn uses this least squares from NumPy, but I will look it up. But I'm fairly certain. I looked it up at some point.
That's great.
And then I felt bad that I didn't implement it in PyFixest as a default.
Thank you very much. For any follow-up question that I have, I will ask you later.